So we had started talking about section 15.1 last time. And in chapter 15, we've just been talking about exponential functions so far, right? So if you recall, what we said, an exponential function was something that was kind of this form, where a is not 0, b is positive, and not equal to 1. Right? That was our definition for exponential function. So remember that we called b the base for the exponential. Now, you can pretty much pick any number that you want as a base. You could have 0.5 or 19 or 156, or 10,132.6543289612537821643782435655321784.
Hello, I'm here to steal some of your blood.
Not mine. My students' blood.
Yes, various bloods.
And it's you personally that are going to be taking it?
Oh, it's Teresa and Kairos.
Who?
I think Teresa, is she on Kairos?
Teresa who?
Allard.
Not in this class.
She was on my campus.
You just have the wrong classroom, I think.
Okay, and then Connor.
Aaron said he thinks he's going.
Yes, you are.
I enjoy that you wore the vampire
We got
capes.
capes. To vampires.
Yeah.
All of your blood.
All right. Hi, Domenico. How are you? Cool. Good talk. So these exponent bases, right, can just basically be any number they want. There is one special number that we often use as the base of an exponential. It's called the natural base. Or sometimes it's referred to as Euler's number. And it's denoted with the letter E. And what E is it's the limit as x goes to infinity of the expression 1 plus 1 over x to the x. So what the heck how would you go about doing something like this? Well, let's just kind of show you what we might do. So I'm just going to make a list of values. Okay, that's a bunch of values. So these are going to be our values for x. And you see they're getting really big, right? I have 1 down to like 500 or something, which is going to serve as kind of like our proxy for infinity. So we're going to have 1 plus whatever that cell is next to it, or 1 over that cell that's next to it, to the 1 over the whatever that cell next to its power. And then we can just kind of drag down. So one way to evaluate a limit, if you don't know what it is to just kind of do some testing. So I'm just going to plug in some values. So we start at 2, then 2.25. And if we go down here, we start growing really, really slowly, right? We just keep scrolling, we keep scrolling, we keep scrolling. We're just stuck in the 2 7s here. And stuck in the 2 7 1s. We go all the way down to like 500 or something. We're 2 7 1. Let's just do a super big one there. Do one more. Still in the 271s. So this is a way that you can evaluate a limit just numerically. When you have a computer, it's easy to do this because it doesn't take long for the computer to do a calculation like this. If you're trying to do this by hand, it's an incredibly difficult calculation to do by hand. But the computer handles it no problemo. So it turns out that this number here, E, is an irrational number. So what does that irrational number, the fact that it's irrational, mean?
That means it's like I, isn't it?
That's imaginary, different I word.
It means it's not the number.
Okay, it's not a whole number. That's true. So is like 0.25 irrational? No. It doesn't end. So like 0.3 repeating is irrational. No. No. So irrational means you can't write it as a fraction. So like 0.3 repeating is 1/3. That's fine. Irrational is stuff like pi or the square root of 2, or in this case, e. These are numbers that don't ever end. If they ended, the decimal ended, you could certainly write as a fraction. If you give me any terminating decimal, it's pretty easy to write it as a fraction. But if you have an infinite decimal and there's no like pattern to how the decimal repeats, then there's going to be no way to write as a fraction. And E is one of these irrational numbers. And we'll talk more about E a little bit later when we talk about like exponential, like modeling some exponential story problems. But for right now, we're just going to leave it be. It turns out that this is really important, though, in modeling like systems that are changing all the time, rather than just changing periodically. Anyways, we'll continue on here. So with this new number E, we can redefine our exponential function. We can now say that it's a times e to the kx, again, where a is not equal to 0, and k is non-zero. So what have we done here? Let's go back and look at what our exponential function was originally. Was a times b to the x, right? And b could be almost any number. It had to be positive and non-equal to 1, but... And now we've changed this so that our b is basically this e to the k part. And the nice part about that is since e is a fixed number, it's that number 2.71, yada, 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 yada. And k is the exponent. K can be anything other than 1, and it still is going to meet the criteria from before. So just like a little less restrictive. Okay. So when we talk about these exponential functions, there's basically two types. So either way we're representing it. So we say if A is positive and either B is greater than 1 or K is greater than 0, this is going to be called exponential growth. Good luck! I hope he doesn't faint or anything. Sometimes people faint when they give blood. Sometimes just from like being stressed out, and sometimes from just like getting lightheaded because they took a lot of your blood. Anyways, and then if that A is positive and then B is between 0 and 1, or K is negative, we call this exponential decay. And it'd be worth pointing out then to say that if the A value is negative, which it can be, that's okay. Those names would be, the criteria are flipped, right? So if A is negative and this, then this is growth. And if the A was negative and you had this stuff, this would be decay then. Is that all right with you guys? That basically, if the A is negative, then the opposite is kind of going on. Yeah? Okay. Let's do it this way. Put you over there. So let's look at, or the natural place that we look at exponential growth and decay is really with like story problems. So let's look at an example, and rather than me writing these examples, I'm just going to copy and paste them in because, well, I don't know, I just don't want to do all that writing. Make that a bit bigger, huh? Sure. All right. So, given that a population of a certain city in 1990 is 782,248 people, that's a precise count, and the population of the same city in 2000 is 895,193, and assuming the population growth is exponential, in what year will the population reach 1 million? So we're told that the population growth is exponential. Everybody agree? So I'm going to use my exponential model. I can use either one. I'm going to use the standard one that we started with. Everybody's okay there? So we mentioned earlier that B was, we called the base of the exponential. Do you guys remember from last time what we called A? We called A the initial, oops, spell it right there, Kulik. Yeah, the initial value. Good. So, in this problem, what would the initial value be? Yeah, I agree. Because that's the, essentially for us, is basically like time zero. Right, that's essentially when the problem starts for us. The 1990 is basically like time zero. Everybody cool with that? So we still need to figure out B, correct? How are we going to do that? Well, we're told this. This is essentially another point, right? Where the x is going to be the time. So what would the x coordinate here be?
So x is the time, so 2000.
Well, it wouldn't be 2000 if 1990 is times 0. Yeah, let's make that 10. Is everybody clear as to why 2000 is turning into 10 here? Just 10 years after the start of the problem. The problem starts in 1990. 2000 is 10 years later. Right, you could do 1990, but then for x, but then 782,248 isn't the initial value, and it becomes a more difficult problem if we just kind of assume the problem starts at year 0 instead of whatever the date is. Then it's simpler to handle that way. Is that okay, Leo? Okay. So my y coordinate is that new population. Oops. My x coordinate is 10. So I just need to then solve for b. Everybody's okay with that? What would the first thing I would need to do here to solve for b?
Well, you probably get B along.
Yes, very good.
So let's subtract that 782.
Okay, is that 782,000 and change being added to b?
No, it's being multiplied, so divide it.
Yeah, so let's divide. Good. Everybody on board so far? Okay, now what should we do? Gotta get that b by itself. Right now we have b to the 10th instead of b. How are we going to get rid of that exponent of 10? We talked about this last year in our Algebra 2 course.
Log.
Not a log. A log would be if the variable was in the exponent, right? Where is the variable though in this problem? It's the base of the exponential, right? So if you had 10 to the b, that's a log problem. B to the 10th is not a log problem.
I don't remember.
Well, if it was b squared, what would you do?
Square root.
Okay. Do we have other types of roots?
Okay.
Yeah, we definitely do. What kind of root do you think we're going to use to get rid of a 10th power? Yeah. So what that looked like was we put the 10 in the little
Oh, yeah.
check mark there, right? And because this is an even root, what do we have to remember when we do this to both sides? We get a plus or minus, just like when we square root both sides. The index for a square root is 2. The index for the 10th root is 10. Since they're both even roots, they both get plus or minuses. Lily?
Then what if it was an odd root?
Then you don't need the plus or minus. It's just whatever it is. Worth pointing out, with an odd root, you can do the odd root of a negative. Unlike even roots where you can't do the even root of a negative number. Odd roots, it's okay to do the odd root of a negative.
You don't have to have an I there?
Nope, not for an odd root. And that's because if you multiply 3 negative numbers together, you get a negative. So it's perfectly reasonable that you can take the odd root of a negative, right? Okay. But what do we know about this number b? It's the base of an exponential. So what kind of number does it have to be? Yes. Remember, b is always positive, so we can drop the plus or minus because it's just going to be the positive. And now it's calculator time. All right, who remembers how to type a 10th root into their calculator? There's 2 ways you could do this. One way is you can press the math button, and if you notice option 5 there, has the square root with the x where the index is. So I can go back and change that index to 10. And then I can do like my fraction command and do 895,193 divided by 782,248. I get that. So the other way you could do this is you can do the division. And remember that, you know how like we talked about a square root being the same as a 1/2 power? We talked about that last time, right? Ring some bells. So a 10th root is the same as a 1/10 power. So I could also type it in as just like the fraction to the 1/10, and I'll get the exact same number. Either way of doing it is fine. They mean the same thing. So that's how you type that into your calculator. Is everybody okay with that? Hopefully ringing some bells. Okay, so we have our value for A, we have our value for B. Let's do that so I can still see. So 101,357,8,108. So our function then is 782,248 times 101,357,8,108 to the x. So that's our model. But this question is asking more than just what's the exponential model. It asks, in what year will the population reach 1 million people? So what is, which part is representing the population? Well, so we have an output or an input, right? Where's the 1 million going to go? Is that the output or the input for our exponential function?
What was the X? Did you say the X was?
Input? It is not. Yeah, so this is the output. That's the population. The X is the input. That would be the years or the time. So if we want to know in what year will the population reach 1 million, we are putting 1 million in for f of x. And we're going to solve for x. Is everybody okay with that idea? Now, as Leo had pointed out, and we had mentioned earlier, if we're going to solve for this algebraically, what would we have to use since the variable's in the exponent? A logarithm. Have we talked about logarithms yet in this chapter? No. What was the title of the chapter again? It was like exponential and logarithmic functions. Do you think I'm going to break out a logarithm to solve something that when I haven't even talked about what a logarithm is yet? When it's in the title? No. So we're going to solve this with our calculator just by graphing. And we'll revisit these kinds of problems later on in the second part of the chapter once we've talked about logarithmic functions and how to use that to do this algebraically. That was fast.
Yeah, they couldn't take my blood because I got a cold.
Oh. Those vampires are very discerning.
Yeah, they are.
What's up?
What's another? What the Y?
Pop. Oh, years. YRS. Sorry. Yeah, if you can't read something, feel free to ask, you know. Like, I know my penmanship is sometimes, like, not always that great. So if you can't read something, no problem. Just ask, man. All right. So let's talk about how I'm going to type this into my calculator to solve it. Everybody good? All right. So to do this, I'm going to use the graphing function. So I'm going to go to my y equals menu. Into y1, I'm going to type in one side of my equation. So in this case, that's the 1 million. 1, 2, 3, 1, 2, oh, I should clear all that. Okay. 1, 2, 3, 1, 2, 3. Emilio, hi.
Hello.
That's all.
Good morning.
Good morning. Everybody cool with that? In the y2, I'm going to type the other side of the equation. So 7, 8, 2, 2, 4, 8 times 1.013578108 to the x. So far, so good? Okay. So now I'm going to set my window before I hit graph, because hitting zoom standard on this is probably not going to be real helpful, because this is now a story problem where the x and y's have like real values. So let's go. Yes.
Did you put the X in your equation for the Y?
For the y, I did f of x instead of y equals, but like it means f of x and y are really the same thing, right?
Okay.
Is that what you're asking?
Yeah, well, in the lower equation. Right
Oh, yeah. So I have this, and then I have like to the x, right? So I did exponent and then put the x up there. That's what you're asking?
Yeah.
Okay, no problem. All right. So let's think about the window range here. So let's go back and revisit this actual problem. So when we said 1990, 782,000, yada, 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 this was basically like the 0.0782 or 782,000, right? Everybody's cool with that? So my x minimum is going to happen at 0. Everybody feel good there? Okay. And then we also included the point 10 and 895,000. So I know the x max has to be at least 10 because we're not yet to a million. Everybody agree? So I know the x max needs to be bigger than 10. I don't know how much bigger than 10. Anybody want to just throw out a guess?
15.
15? Well, we went and we basically picked up 100,000 there. So I would guess at least probably 20. Right? Because we picked up basically 100,000 going here. We need to pick up another 100,000 to get to a million. I'd probably go over that, though. I'd probably do 25 or 30. You'd want to overestimate something like this is usually good. Maybe we'll do 25. Did you guys get what I'm looking at when I made that estimate? I'm just trying to ballpark it. You're never going to guess like right on, and you'd always want to guess higher than lower. They go up by 5s or something. So 5, 10, 15, 20, 25. Yeah, that sounds good. All right. The y minimum. So what's the smallest y coordinate that we know about? Well, that's this one that's happening at 0, right? So I'm going to pick a y that's maybe a little bit smaller than that, just so that I can see that first part. I'm going to do 750,000. Everybody's okay with that? The next y we would want to consider is this 895. And eventually the last y we need to consider is this 1 million. So I need to pick my y max to be something probably bigger than a million. Everybody's okay with that? So I don't know. I'm just going to pick 1,250,000 because it's kind of a round number. Everybody's cool with that? And then we'll go up by like, I don't know, 100,000s or something. Is that too many zeros? No, that's the right number of zeros. So hard to count those. All right. And now I'm ready to hit graph. So this is my line for 1 million. This is my exponential curve representing the population. And the solution that I'm looking for is this intersection. Is that okay with everybody? Now, when I'm picking my window, did you have to pick the exact same window that I just picked? No. What's the only thing that you need to see when you hit graph? I just need to be able to see the intersection, right? Any window is fine as long as I can see where those two things are crossing. Are they going to cross in more than one place, Mr. Kulik? No. It'll always just be one place. As long as you can see the cross, then your window is fine. You know? All right. So how do we find that intersection with our calculator? Yeah, second trace. And then the command we're looking for is the intersect command. Boy, they're really hitting you over the head with that one. And now this is the intersect command requires 3 inputs. It wants to know what 2 curves am I finding the intersection of, and then can you give me a guess? How many curves did we graph? Just 2, right? We did y1 and y2. There's nothing else going on in our calculator. Everybody agree? And how many times are they going to cross?
Once.
Just once. So I don't even have to worry about this. I can just press enter 3 times and the calculator's just going to do it. Because after I hit enter once, it changes to the second curve. See how my cursor moved down to this one? Press enter. And the guess, because there's only one intersection, you guess anywhere you want. It doesn't matter. The calculator's going to find it. And there we go. So I get 18.21, 1 million. Hey, what is going on, you stupid thing? Do you see that? I keep scrolling down and just like, no. Okay. So what does 1821 mean? What is year 0 in our problem? 1990. So this is 18.21 years later. So what year would the population be at least 1 million?
2008.
Nope. It would be in 2008, the population would still be less than 1 million, right? Because it doesn't get to over 1 million until after 2008, right? So if you're rounding up, if you're only taking your census like every year, the first year you recorded a population of at least 1 million would be in 2009. So this would be, even though you'd think from our normal rounding rules you would round down, the context of this problem is telling you really, no matter what, you're rounding up. Does that feel okay? Cool. And these are the same, we've done these last year, right? Is this starting to ring some bells with how to do this in the calculator, do the graphing thing? We did this last year. So, all right. We have one more topic to look at and to do some examples on, and then I'm going to be done here for today. Sound cool? This is going slower than I thought it would, but that's okay. You know, we're taking our time and being careful. So the next one, we're going to define something called a logistic growth function. Whoa. Did the lights all just flash on you guys? Okay. I just didn't know if I just had like a moment there or something. I'm glad we talked about it. Angela. Of course, yes. There did it again, right? Okay.
Maybe we could go home.
Yeah, maybe.
Wait, so if the power goes out, do we go home?
No, that's happened before and we just sat here.
Yeah, depressing. You're watching a movie in my class now.
Okay. So if we have some positive real numbers, A, B, C, and K, where B is between 0 and 1, we say that a logistic growth function in terms of x is of the form f of x equals c over 1 plus a times b to the x, or if you prefer the other form of an exponential, c over 1 plus a times e to the negative kx. We call that numerator c the limit to growth. And if the b was bigger than 1 or the k was negative, this just becomes a logistic decay function then. So we have both growth and decay. So the thing that's important about this is that these logistic growth and decay functions, they have two horizontal asymptotes. One of them's going to be the x-axis, and the other one is at y equals c. So what is this going to look like? You have like a y equals c here, and you have y equals 0 down here. And our growth function is going to kind of look like this, and our decay function is going to kind of look like that. Why would these things be important? Well, there's lots of real-world systems where there's a distinct kind of like lower bound and upper bound, but in between the things kind of grow exponentially. So if you think about a population, right? Say like you have a petri dish with bacteria in it. The minimum population of bacteria on your petri dish would be 0, right? Like if there's no bacteria there, you can't have negatives. And there's going to be an upper bound, right? Because eventually the bacteria is going to cover all the space on your dish, and or there's not going to be enough food or resources or whatever for the bacteria to eat to keep reproducing, right? So there's going to be like some upper bound to the population there also. The same thing exists kind of in nature, right? At some point, there's just going to be too much of some animal because there's just not enough food or places to live or whatever. So there's going to be like an upper bound to the population, right? So there's lots of kind of real world scenarios where there's a distinct lower bound and upper bound, and like in between things are going to grow exponentially. Joe.
Okay, this is on topic but a little off topic. That picture that you drew, there's like cryptocurrency, there's a trading strategy called MACD where it kind of emulates what that looks like over this intersection.
Okay.
You can use it or help use it to predict the price after looking at the graph. Can you use these? Like, is this predicting something? Sorry, really off topic.
Yeah. So we'll look at a instance where we're going to use this function to look at in a real world context in a moment. So if you're building a model, then you'd use that model to predict something, and that's kind of what we're doing. But before we do that, let's just kind of do a little bit more basic example to kind of get used to what this looks like. So let's say we have some logistic function here. So first of all, is this growth or decay? Is this logistic growth or is it logistic decay?
How do we know?
We're going to know by looking at the base of the exponential. So this is growth. It's the opposite rule as exponential growth and decay, because notice where the exponential is at. It's in the denominator of the fraction. So when it basically means the rules are reversed. So this is growth. Maybe we'll say logistic growth. Let's be specific, right? And I'll write down the reason. What are the horizontal asymptotes going to be here? One of them is easy because it's always y equals 0. Howdy, sir. The other one is it's y equals c, and the c in this problem is 10.
Is that always the case? The c will be the numerator?
Correct.
What if you have multiple things in the numerator level?
Nope, it'll just be a number.
Just gonna be one. Okay.
Just be one number. Okay. And what would the y-intercept here be?
Actually, jumping back to see if that's plus.
Okay, no problem.
Would one of them be 1?
Well, the x-coordinate for all y-intercepts is so here's the y-axis, right? So some point on the y-axis,
So 0.
x-coordinate has to be 0. So when I plug 0 in here, what's 0.6 to the 0? No,
Or
1. So that just is gone, basically, right? So I have 10 over 1 plus 3. So 1 plus 3 is 4. I have 10 over 4. Or you could reduce that down to 5/2. Or if you wanted to call it 2.5, that's okay also. Everybody okay with that? Let's look at the graph now on our calculator just to kind of see what this is going to look like. Get rid of that stuff I had before. So 10 over 1 plus 3 times 0.6 to the x. And we just had messed up our window real bad, so I'm going to go back and just do a zoom standard here. So there's our graph. Everybody's okay with that? Kind of looks like the blue one that we've drawn up here, right? It's kind of that S shape, right? Kind of looks like a squishy ducks. S, like a snake. Sometimes you get a little lispy in the morning, and the X's and S's all kind of sound the same. Does that ever happen to you? No? You guys make me feel weird sometimes. All right. So let's look at another example here. Quite a similar problem. So the previous example that we had, story problem example we looked at, was a exponential growth problem, which was probably unrealistic because we know the population of a city is not going to grow without bound, right? There's really only so big a city can get because there's only so much geographic area that people can settle in. And yes, you could build up, sure, but there's a limit to like how many services you can kind of stack in there to deal with so many people, right? It's pretty tough to get a city that's like, you know, like if it was going to be like 50 million people in this city, it's like, yeah, right. That's just, you know, just not going to be realistic. So here we have the population of a city can be modeled using the logistic growth equation shown below, where P is the population of the city T years after 1950. At the beginning of what year will the city have 1 million people? So this is going to be the same basic problem as before, right? So I'm just going to take 1 million and plug that in for P of T. And then we're going to be solving for the T in this case, right? Everybody's feeling okay? We'll do this the same way, so we'll just go and type this into our calculator. I'm going to clear out the thing that I had in there. In Y1, I'm going to type in that 1 million. So 1, 2, 3, 4, 5, 6 zeros. Into Y2, I'm going to type in my right-hand side. So I have 1,425,397. That's apparently the upper bound of the city. It's pretty precise. And the denominator, I have 1 plus 21.783 times E. Remember how to get the E button on your calculator? So you press second and then the LN button here on the left side will get you that E with the exponent on it. And our exponent is negative 0.04982. And then T is our variable. I'm going to put X there because that's the variable button on our calculator. We'll need to reset our window. So again, 1950 is occupying as basically year 0. And I don't have any idea here. I'm going to give it 100 years. I'm just going to guess. Again, my minimum, we're going to go 0. And our maximum, I'm going to do like 1,500,000. Is that the right number of zeros? Yeah, okay. And we'll go by 100,000s. Okay, hit graph. So there's my 1 million line. Here's my logistic curve. Woo! Almost took a long time to get there, but that's okay. So if we hit second and trace and select the Intersect Command. So again, we only have 2 things graphed, and there's only one intersection, so I'm just going to do 3 enters, and 79,000. Boy, that's pretty good at 1 million. So what does that mean? 1950 is basically year 0. So I get 2029.
Wait, why is it in 2030?
Because it was 79.0, right? Because it was like dead on.
So if it was 79.01, would you still go to 2030?
I would say I would try not to give you a problem where it was that ambiguous.
Okay.
Right? Like we'll have something in the 10 spot at least if I'm expecting you to round all the way up.
All right.
How's that sound?
Sounds good.
Sounds fair?
Yeah.
Yeah. What you're talking about now is just like you get into like the margins of like when does this matter and when doesn't, like how close is close enough. Yeah. So I'll make it obvious that there's like definitely something in the 10 spot.
Okay.
for that kind of situation. That's it for section 1. At this point now, you guys should be able to do up to problems. Let me double check, and before I say something wrong, everybody gets mad at me. 16. So I think I'd asked you guys to do 1 through 8 already, so we'll add that up to 9 to 16. We'll put this on to the week after next problem set, right? Since we won't have a chance to talk about this one before Sunday. We'll push this into next week. So right now, Sunday's problem set is just 1 through 8. What a whimper. You guys don't mind though, I'm sure, right? All right, we'll stop here so you guys can start on the homework or whatever's highest priority thing for you.